So back to our theory. What I call theory and what the mathematical statisticians call theory are entirely different beasts. So processes, I'll work through this vector of matrix of Poisson counts that's where the Poisson parameters are generated by gamma processes. The same theory actually works for all the standard processes you read about. In the recent literature, there's a lot of people using beta processes, negative binomial processes, which are rather like Poisson processes. A lot of these things are used in matrix factorization, in recommender systems. So there's a big literature here. And also in some of the knowledge base work. So there's a pretty big and growing literature here. So first off, this is just a big picture of what's happening. So we won't go into the details, the mathematical details yet. I'm just trying to give you a map of everything before we get into the details. Now, there is a very comprehensive review by these two guys. They're bona fide Bayesian non-parametric statisticians. This is very heavy going. We've actually done some of the definitions you need already to work through some of this stuff. I can get through about half of it. And that's after my month of study. So God help the regular person from machine learning or something or other. But it is a review of a lot of the literature that can be done. So remember our spatial processes. We had a process part and a marked part. The process part is generated with our Poisson processes, and the marked part is just another thing we add on to add. So in our case, the process part is going to generate an infinite vector of weights or probabilities. That's what we use it for. The marked part is going to be the objects. That is the objects of our mixture model. Whatever it is that we're mixing with the process part. This is what the process part looks like. This is what's called a gamma process. Now, if your integration is current, you'd look at this and say, wow, that integrates to infinity. Won't integrate. So that means it's not you cannot normalize it and get a probability density. And these are different values. So remember, with a process, we can scale it anyhow we like. It doesn't have to go to, doesn't have to integrate to anything finite. So what happens is, because of this lambda to the -1 component, it's infinite at 0, and that's where so when we generate an infinite vector of these, a countable vector of these lambdas, using our Poisson process, we're going to get an infinite number near 0. But at any finite point away from 0, there'll be a finite number. So there's a finite number greater than 0.1, a finite number greater than 0.01. But there's always an infinite number near 0. And that happens because the integral diverges near 0. But the way we use this infinite vector, it doesn't matter that there's an infinite number near 0, because if I say, well, the probability of this is 10 to the -35, you're going to say, oh, I don't have to worry about it then. I can forget about it. It's so small, it's not going to be a problem. So we're going to have our infinite number of these parameter vectors is going to be in the ignorable range. And it's only the ones that are a bit bigger that we have to worry about. So that's why all of this works, and we'll look at how that works in the next couple of slides. But all the rates that we're going to use have this form. They're all infinite near zero. At zero, they're infinite. But they still work as Poisson processes because we just break up our domain into integrable slices and generate the number of points we need. And as long as we don't go all the way to zero, we're fine. Now, remember the axiomatic definition for the Poisson process. We have exactly the same axiomatic definition for the gamma process. We replace Poisson by gamma. That's it. Same thing. The only thing is the gamma process, instead of generating counts, it generates real values. So it's a real valued thing. And it can either be defined axiomatically like that, or we define it with this rate. And the mathematical task we have is to show that these two definitions are the same. That the axiomatic definition from our additive distribution is the same as the Poisson process definition from the rate. And that's an important bit of theory that we'll look at briefly. So how do we know these are the same? Well, we'll see. There's a formula that links them. How do we do statistical inference? Well, it turns out statistical inference with this rate is actually quite easy. And I'll give you the basic outline for it. So all of these processes that you read, well, all the ones we read about, there's another class of processes called the Hawkes process, which have quite a different form, but all of these others fit into the category I'm talking about today. And remember that diagram, if they're at the root of the hierarchy, what it's generating is an infinite vector. An infinite vector of parameters for us to use. Below the hierarchy, it's actually a completely different beast. In the Dirichlet process case, it's just acting like a Dirichlet distribution. In the gamma process case, it's acting like a gamma distribution. In the stable process case, it's acting like a gamma distribution. I hope you get the pattern there. So I'll give you an example. This is the formula, by the way. So here, using that rate and our Poisson process machinery, we generate an infinite vector. But below that, we're not inputting a generic distribution, a Gaussian or something. Instead, we're inputting a discrete distribution. And if you remember, if we applied a process to a discrete distribution, we apply it pointwise. So if we're mapping from mu to lambda, where is that? What we're doing is pointwise. Mu k is mapping us to lambda ik. Lambda k. So below the root of the hierarchy, everything is just vector mappings. It's no longer processes. And these two interpretations, they nicely complement each other. Now, what's missing here is I meant to add an introduction to the Pitman-Yor process. So in 2006, Wray Buntine, who was the guy on all the earlier papers, he realised that language models as in the, I'm looking at Nessonay. The Nessonay language models, they behave somewhat like hierarchical Pitman-Yor processes. And Nessan knows more of this than me, but now I spoke to Wray about this. He said, oh, that's just a funny little thing we discovered. You know, it's not practical. But just to show how it can be practical, we're actually using Dirichlet processes now. We use them to do smoothing of Bayesian networks, and we're getting the best results for Bayesian net classifiers anywhere. In fact, we're now beating decision forests quite handily, which is the go-to method for data science now. If you want to do well, you use decision forests. So we're actually beating them by using Bayesian classifiers with Dirichlet processes. And the probability results you get are incredibly good. So the probability estimates at the leaves are really more accurate than other methods. And that's an example of this stuff going on below the hierarchy, where we're doing the inference well. It also shows you can scale it up quite well, because one of the features of this is that we can run on hundreds of gigabytes of data where decision forest falls over and won't work. So, so when Wray was saying, oh, this is just a little oddity and it seems to look nice, but it doesn't really scale up. You can scale this up if you apply it right. Now, so he was doing a Pitman-Yor processes for his language model. A Pitman-Yor process is a Zipf-in extension of a Dirichlet process. Now, what I figured out using this theory here, this kind of theory, was what a Pitman-Yor process actually looks like. And so at the root node, it's generating an infinite vector. This complex expression here is actually what the distribution looks like below the root node. So to me, this is kind of new. It's pretty horrible. Let's just say it's horrible and stop at that. But it is a formula, and you can generate curves with it. So you can get to see what the distribution looks like. So the red curve is the Dirichlet process. It's actually a beta distribution. You can just see it here. And the yellow curve is the equivalent Pitman-Yor distribution with exactly the same mean and variance. And what's happening is it's a lot more biased. So the Dirichlet process, the Dirichlet distribution version is a lot more symmetric, and the Pitman-Yor distribution version is a lot more biased. So there's another example with a very low mean. The mean here is 0.01. But that's just showing you can develop this stuff all the way to give sort of interesting results. So what are we doing? We're working with these feature matrices. And we've got our favourite matrix. Each column has a parameter associated with it that's generating the data in that column. And, our process with our rate is generating this infinite parameter vector. Infinite meaning countable. And then we've got objects attached, which is what we're doing our mixture on. So there's objects attached to each column as well. What we'd like to do is some sort of inference where we're, say, estimating the values of these parameters, or this might be latent data, like in a hierarchical model, in which case we're also estimating how many of these are non-zero. So the gamma Poisson model, it's a generalisation of LDA. It's the standard count matrix factorisation model that's used in recommender systems. The entries here are counts instead of 0, 1s, instead of booleans. When we set it up, we've got a fixed k. It may be unknown, in which case we're doing parametric inference with an unknown k. And we're always given a fixed number of documents or images that we're processing. But we might not know how many features we have. So that's the original model, and there's a gamma distribution put on these lambdas, and there's a Poisson distribution put on all of these points based on the gamma at the top of the column. So that's the model. Here's how we generate data. We generate our number of columns, our number of features k from a Poisson. Then we generate our parameter vector according to a gamma. And then we generate the data matrix. So we're according to a Poisson. So it's called a gamma Poisson because there's a gamma and a Poisson. So that model is used pretty widely. We're now going to modify this for processes. So we're going to make k potentially infinite. So, but to do that in sort of a finite achievable way, we're going to change k. K is now, instead of some unknown dimension, k is the observed non-zero data. So we order our features so that the non-zero columns come first, and then we count them. So k is now our non-zero observed amount of features. And what we're going to do is put a rate on k. That rate will come from our process theory. So the only difference here is before k was just some fixed value and we maybe generated it with a Poisson rate. Now k is determined by the data, and it's specifically the non-zero features in the data. So that's our difference. And here in orange I've marked the differences in that in the generating algorithm. So now k is the number of non-zero columns. Previously it's just the amount of columns, and some of them could have been 0. Now here's where the Poisson process theory comes in. It's going to say that the more documents you have, the more likely it is for you to get more non-zero features. So if you've got 100 documents, you'll get a certain amount, maybe 10 features on. If you've got 1,000 documents, you might have 100 features on. So the more documents you get, the bigger I, the bigger k is going to be. Makes sense. As you get more documents, you get more words in your dictionary. We all know that. So that's the kind of process that's going here. And the Poisson process theory will give us a formula for that. Next, we generate our parameters. But now, we're not just... Our parameters are informed by the fact that we know the columns are non-zero. So we can actually do a posterior inference there and say, instead of just generating them according to a gamma process, which we know has infinite at 0 and it's not a probability distribution, we can't generate lambda. If we know that we've got non-zero data, that skews everything. Remember, if lambda was 10 to the minus 30, it's going to generate zeros. So that value of lambda we can forget. And when we generate our data, we also have to make sure that we generate no non-zero columns. This is what these lambda i's look like, according to the Poisson process theory. We'll look at the formulas for these at the end of the tutorial. Some are simple, some are complex. If your Indian buffet process theory is up to date, you'll know this top formula. The thing to note is that this is order, is the general order. This is order log I. So here are what generally happens. The non-zero rate is going to be order log of the number of documents, or order I to the alpha, where alpha is less than 1. So it's the number of features is always going to grow less than linearly with the number of documents. This is the Dirichlet process case, the gamma process case. This is the Pitman-Yor case, which is Zipfian. And this is how, remember, this is the formula for generating the lambdas here. And we've modified it because we know that the data there's non-zero in the column. So if we do that, it actually changes. If you remember, the gamma process went to infinity at 0. None of these do. This one actually does eventually hit the y-axis here. As you add more data, what happens? You can get smaller and smaller lambdas. See, the purple one it's got more weight in the lower end. So as you get more and more data, more documents, more images, your non-zero rate says you can now have a smaller lambda. And this formula, again, we'll look at where this comes from, is created from the process theory. So first off, we generate the number of non-zero features, and that comes from a non-zero rate that the theory gives us. Then we generate the parameters associated with those non-zero features. And that comes because knowing it's a non-zero column means that infinite weight at 0 has disappeared, and we now have an integrable rate. I actually find this really, really remarkable. I think it's wonderful theory. It's all derived from the Poisson process theory. You can't use any old formulas. You use particular ones. All of this comes from a paper Lancelot wrote in about 2013, but he published, Lancelot James, but he eventually got published in 2016. He's got a much more complex way of doing this than me, I should add. And his formulas are more complex. I figured out some simplicities. I figured out early on that if you simplify stuff, it becomes easier. Right? That's the big take-home lesson I hope you got from undergraduate theory. You realise you've got to simplify it if you want to remember it and understand it. Now, there's something called completely random measures and normalised random measures with independent increments. And this is how all of this stuff is done in this framework. You can read about these in the Lee Joy's summary article. I won't go over this here. We'll skip this section of the tutorial. So if you want to look at it, download the tutorial and have a look at it. It's in all of the introductory papers. Usually there's a page summarising very tersely what it is. We'll have a look at some of the major processes and then we'll get into the various theory results. So a beta process comes from a beta distribution. There's a beta distribution, which is a Dirichlet of order 2. Here's a beta process. Similar formula for theta, but now you can get less than -1 alpha goes negative. Ugh, God, sorry. So this is a rate and no longer a probability density because it doesn't integrate. And it's rather like what we call an improper beta with a minus value here. But that minus can't be less than or equal to -1 because after you've seen one bit of data, it has to become proper. So once you've seen one bit of data, this wants to turn into a beta distribution. Here's the gamma process example. This is called a generalised gamma process. There's the gamma distribution. Here's the gamma process. Again, there's this lambda to the minus alpha minus 1 there. And this is rather like an improper gamma minus alpha beta. And once you've seen one count in your Poisson, this gamma process rate becomes normalisable. There are the general formula. There's also something called a stable process, which is actually the granddaddy of them all. It's very important. So the beta process, that integral doesn't work, and that's because of this theta to the -1 term. However, if we multiply this by theta, that theta to the -1 term disappears and we now get a beta integral and it all works. There it is. What that means is if you've seen one data point, then your probability, you get a probability vector on what those values in your infinite vector can be, and there it is. Same with the gamma process. For a gamma process, we've got Poisson data. And for Poisson data, seeing a non-zero data point looks like this. 1 minus e to the minus lambda, because e to the minus lambda is zero data. So 1 minus e to the minus lambda is non-zero data. So if we do this, multiply our rate by that, we've seen non-zero counts. We now get something that becomes a probability distribution. We can integrate it. Now this is a bit of a tricky integral. So you have to use integration by parts. It's a bit complex. So it would be an advanced question for first year undergraduate doing integration. So when we've got these rates here, this is what we can do. We can sample our infinite vector. But that's going to be a bit tricky because remember, in the infinite vector, most values are arbitrarily close to 0. So the first point we get is going to be 10 to the minus 1,000. The next point will be 10 to the minus 1,000,000. Right? Because they're all but a finite number of them are arbitrarily small. So we can't just sample this in any way. We've got to do it carefully, and people sample it by size. What happened here? The other thing we can do with these is normalise them and get ourselves a probability vector. Handy thing to have. And final thing we want to do is inference based on the matrix of data. So they're the things we'll be looking at now in the main theory. So this is just some of these. I'm just citing results, which good luck to you if you want to find out where the original sources are. I've managed to get some tutorial slides from Lancelot and gone over them to dig out the details. But you know, it's like this business of these formulas we got from Pitman's paper. He's got a 500-page book he wrote, and there's probably more than 500 formulas in that book. And those formulas are written in a completely different way to what we would want. In many cases, it's not dressed up as a prior or posterior or something. It's just an arbitrary combinatoric somewhere. So finding these results from their theory is really hard, is what I would say. But if you go and ask them this, what's this? Well, obviously, you know, they'll point you to the results. So, main theory, so total mass. The first thing we want to know is what's the distribution on this total? Why is this important? It's the main thing. How do we know that the gamma process, which has this particular gamma rate, gives us gamma distributions on the finite parts of the space? How do we know that the Dirichlet process gives us Dirichlet distributions on the finite part? So that link is produced by this total mass. This is a case of a magic formula I'm going to give you. Comes from Poisson process theory. We can't actually get the distribution directly, but what we can get is the moment generating function. If you've done first year undergraduate stats, you would know what a moment generating function is. That probably excludes most of you. If you've done first year engineering, a moment generating function is virtually a Fourier transform. And it is actually a Laplace transform. So that is to say these are quite well-known things, but you may not know about them. If you take the log of a moment generating function, you get something called a cumulant generating function. Those statisticians do all sorts of stuff. There's very good entries to this on the Wikipedia. In fact, let's see this. It's popping up here. Oh, they're seeking money. You know, every now and then I take $50 out of my account at Monash and I give it to Wikipedia or some open source. There it is. So there's the definition, expected value of t to the x, where x is our variable. And we get formulas like this. The moment generating function is the middle one. And that is a way of characterising the distribution. So here's the result. Let's just say it exists, right? It exists. You don't have to... I mean, in this short tutorial, you're not going to understand this formula. I've put it in there so you can get it if you want to. But there's the calculation we do. It's a bit of a tricky integral. You've usually got to use integration by parts to get it working. And it comes from some magic thing called the Levi-Khinchin formula. And it applies from Levi processes, where you can look it up. The result is actually not that difficult to derive, but only if you don't want to do it formally. So if you look in any textbook in probability, I looked in some probability theory textbooks and you get pages of measure theory and you just kind of forget about it. Can't do it, sorry. But Pitman, in his tutorials he gives to his second year statistics class, which are all on the web, has a lovely 4-line derivation of this formula. So it is pretty simple, just if you're not going to be formal. Using that, we can look at these processes and figure out the distribution. So the total of the vector for a gamma process is in fact a gamma distribution. What a relief. For the generalised gamma process, it's something called a Tweedy distribution. For a stable process, it's a positive stable distribution. And this is a tricky one that Lancelot had to do for me, is a beta process, you get something called a Dickman distribution. So these stable, and a Tweedy distribution is actually derived from a stable distribution. They're quite magical things. And this is how I got the Pitman-Yor distribution from this. So that is to say, we can get the distribution for these things and prove our link between the process and the other side. So the next thing we're going to do with our infinite vector is normalise it, divide it by this. We'll just list some of the cases. No one bothers normalising a beta process because it's not used that way. A gamma process, we get a Dirichlet process. A generalised gamma process, we get something called a normalised generalised gamma process, an NGG. A stable process, we get a Pitman-Yor process with a concentration of 0. Now, these are the ones that Wray Buntine and his group used with the memoizer, which was a very nice text compression algorithm they produced. It was very competitive. So that is to say, we can figure out in many cases what these distributions are. What about the Pitman-Yor process, which is really an important one? We'll get to that afterwards. The next thing is equivalences. Now, early on I said if you normalise a gamma distribution, you get a Dirichlet distribution. Well, if you normalise a gamma process, you get a Dirichlet process. If you normalise a stable process, you get a Pitman-Yor process in this way. And if you normalise this generalised gamma process, you get a Pitman-Yor process, and the total is a gamma. So these equivalences are how we map from, I think I give it next, yes. So remember I was saying that this hierarchical Poisson matrix factorisation is in fact identical up to some minor little term to a hierarchical Dirichlet process. Here's another one where I'm guilty, a robust negative binomial Poisson factorisation. Who'd know is exactly the same as what we did in 2014, a bursty LDA. So there's lots of times where you can recognise these equivalences. You know, this really means something because what it means is algorithmically, experimentally, we have to compare which algorithms are better. And my bet is that one algorithm is going to blow away the other algorithm. So no one's done these comparisons. This is why this is important. No one's gone to find out how they compare based on those equivalences. A Pitman-Yor process is a bit more complex, and this is the proposition 21 that I railed about at the beginning. We take a generalised gamma process, we normalise it, and then we integrate out the concentration parameter. So it's a bit more complex. We've got 2 steps to do. If we do, we get a Pitman-Yor process. Okay. Some stuff about equivalences. So these are the sort of main results. Sampling. How do we sample? We've got an infinite vector, and almost surely any sample we take is going to be less than epsilon for any epsilon. Get your head around that. For any epsilon, any sample we take will be less than it. So they're arbitrarily small. So it's pointless just grabbing a lambda from our infinite vector because it's going to be so small we won't bother. So instead, let's sample them proportionally to this. So we'll sample a k proportionally to this. What's that? It's going to sample the bigger ones first. So that's what we do. There's a whole theory of this. Now, you would know it by stick breaking. So that's a term you may have heard of. This is where the stick breaking formulas come from. So we sample the first one according to this vector. We sample the second one, ignoring the one we've already picked, the index we've already picked. We sample the third one according to the same vector, but ignore the 2 vectors we've already picked. So it's quite easy. There is a formula for this. Again, I'm not going to go into it, but it's very elegant. It comes from sort of advanced stuff. But here's the point. We know about stick-breaking formulas. And that's what these are. These turn out to be stick-breaking formulas in the case we know. Hierarchical processes. Remember I had this figure up earlier, which is to say this is the hierarchical processes here, according to Dirichlet process. Here is the Dirichlet version, where we say, oh, that's not a Dirichlet process. When it's below the root, it's a Dirichlet. So this is the simpler version. We only use the process version to generate our infinite vector. After that, we've got just a vector mapping with a Dirichlet or with a gamma or some other distribution we know about. So that applies. The hierarchical part of a gamma process is gamma distribution. Hierarchical part of a generalized gamma process is a positive stable distribution. There's all of these things. So, oh, boy, I'm going a bit fast. Oh, well, we finish. You get an early lunch. Now we're going to finish up. We're going to close the loop. So, we've got the distribution on the total, and that required a bona fide process bit of theory. We've got the model equivalences between different processes, and that comes by trawling through hundreds of pages of complex theory, or going and asking Lancelot James and saying, well, which one's equivalent? I did the second one. And then we've got how do we sample vectors? And the case we know is the stick-breaking formulas. Another favourite of the machine learning community. So now we'll look at Bayes' theorem for Poisson point processes. Oh, hang on. We're just finishing off this hierarchical modelling case. So here's our infinite vector. We've generated an infinite parameter vector, generated our data from it, and we've got our objects. So that's what happens at the root of a hierarchy. If you're below the root, what's happening is that some of these elements here are repeated. You've got the same value. In this case, the objects come from a Gaussian or something else. You never repeat when you draw from a continuous distribution. In this case, the objects are coming from a discrete distribution, so they will repeat. So you might say, well, how many times do I see A in that? Well, that's a total. You've got to sum up the lambdas here that correspond to this A. What you're doing is summing a total, and so you actually use the same kind of formulas we did for the total. So there's the link between the discrete and the other version. And this fact that these entries repeat is what this 2006 paper was all about, all the theory of that. But the basic result is that below the root we're doing vector mappings. So for a gamma process, we're sampling lambda k according to these distributions. So the idea is we've got a parent measure and we're going to generate a bunch of lambdas for it. And it's just going to be a vector mapping from mu to lambda, and the lambdas are generated according to these. Now this table is just the total table with some mu's added. So if I go up to here, my total table is here. I just took this and I replaced m by m mu k. Problem solved. So, but this is what the hierarchical distributions are doing. They're doing a vector mapping of vector mu to vector lambda. It's no longer a process. For those who really like complexity, there's a Chinese restaurant version of this. So you would have heard of the term Chinese restaurants if you've studied the Dirichlet process literature. There's a Chinese restaurant for every process. They've all got the same kinds of formulas. They all behave in the same way. You can do that if you want to. We no longer use Chinese restaurants for Dirichlet processes or Pitman-Yor processes. It's too slow. It requires dynamic memory. Computer scientists hate dynamic memory if they can avoid it. That's why Fortran works so well. But this, if you're really into this sort of detail, I can give you the formulas, but I don't think most of you wouldn't be. So now let's look at this. I think this result is magical. It's the key point of Lancelot's paper, but he wouldn't want me to tell you that, right? He's got his own version of what is his key point. Bayes' theorem for Poisson point processes. It's so simple. Well, the hard bit is looking at these rate formulas. Here's the rate for a generalised beta process. And here's our lambda theta. It's got an exponent so that it doesn't integrate. It integrates to infinity. Our thought experiment is, let's just say that we've got one data point and it's positive. So its probability is theta k. So we can multiply this rate. We can say, well, here's the rate at which these thetas come, and then we're going to put a filter on it and toss out those that give us a 0. So we're going to down rate. We're going to reduce our rate by multiplying it by theta. So if we multiply this by theta, all we're doing is we're saying it's the same rate, but we've tossed out the entries that gave us a 0 for our data. So that's a legal thing to do in terms of processes. But if we do it on I samples, if we do it on one sample, it's theta. If we do it on I samples, it's this. That's if you get 1, 0. 1 minus theta to the I is you've got 0 I times. 1 minus that is we haven't got 0 I times. So this says we haven't got 0 I times. This is our new rate under this thought experiment. So we've got I documents and we didn't get all zeros. So our rate becomes this. So what does that look like? Well, it does integrate. Integrating this gives you this rather complex thing here. How do you do that? I hope you can guess. Binomial expansion. 1 minus theta to the I equals. You use a binomial expansion. And then what you get is a whole bunch of beta integrals which give you gammas. So that's this formula. Now this is going to be our non-zero rate. So given I documents, and we haven't got all zeros, that means this is the rate at which that's going to happen. So this is our expected number of non-zero columns. So we can put a Poisson on this and generate the number of non-zero columns. That's what happens. Our infinite one went off to infinity and became non-integral. It becomes this. It's no longer going off to infinity when we do this. And it now has a total that changes. So in this case, here I've upped the exponent alpha. So the green one is our new filtered distribution. It's now a distribution on thetas. It's no longer a rate. So we can now generate our thetas, knowing that it's given us non-zero in I data points. We can do the same with the gamma process, but now it's got Poisson data. It could have negative binomial data, any other kind. That's the probability of getting non-zero data for a Poisson. So we're going to filter these lambdas, this rate, and say only accept those that give us non-zero data on I documents. This is also integrable. This is done with integration by parts. A little bit tricky. And what I didn't do for the previous one, here is the posterior on what our lambdas look like. Now we know they don't give us all zeros. We're flattening out that distribution near zero, and we now get this. And it's now a distribution. It's no longer a rate. So we can now generate lambdas on the assumption it's not all zeros. That's what the distribution looks like for the generalised gamma process. It hits zero at a point, and it's got a total non-zero rate. So this is what that looks like if you put it all together. And this is more or less what Lancelot's doing in his paper. We've got a rate, and we're going to observe some data. And the probability of getting that data has got to be finite, greater than zero. So if filtering based on we know A is true is going to give us a modified rate, and that rate is less than infinity, then our rate on W now becomes a posterior probability on W, meaning it's integrable. We can now deal with it. And there's a joint rate for these guys that is also integrable in a sense. So given this, you can now do posterior analysis on all of these and look at things. And moreover, you can get a rate for getting A, which is what we did here. We're getting our non-zero rate here. So that's the basic result that lets us do all this analysis, and with this everything else comes out. So James solves this using Poisson process partition calculus. Pretty esoteric stuff. Here's how he does it. He calls it generalised linear buffet processes, but it works for the gamma Poisson model, it works for the Dirichlet processes, all sorts of things. Pitman-Yor processes, it all works. So let's look at applying the particular formulas to these processes. And here's our favourite situation again. We've got our data. We're going to ignore the objects for now. We'll just look at this infinite vector. We've already done part of this, but this is the formulas we were looking at earlier. We've now got a finite, a known probability. We can calculate our non-zero rate. What's the probability of the non-zero columns, given we've got non-zero for the I data items, documents, images? Once we've generated K, then we can generate each lambda K according to this, what is now a probability on lambda K, because the integral is finite. and I showed you examples of them. And having got all the lambdas, we can now generate the data. And having got this generating formula, we can now do everything else. This is a likelihood scheme. We can now do everything else, all the inference methods we have in the Bayesian world. So we can get a posterior on K, we can get a posterior on the lambdas, we can get a posterior on everything, so we can do all our regular inference. Surprisingly, I've never seen someone do this for the gamma Poisson model. So all of these papers on this, they use a stick-breaking formula or something instead of these. They haven't. In fact, there's a whole series of papers on this by various people, and rarely do they ever do this in this full way. It'd be interesting to see what happens if you did. This is the formula I didn't get to complete. So I've worked all of these formulas through in this report. So if anyone wants more details on this, I can give you all the formulas in my report. I've just got tables of them, what these various things come out to be. This is the data marginal for the full thing, and this is what Lancelot presents. And if you read all of the Indian buffet literature, you'll see it's exactly the same thing. I apologise, I haven't got any worked examples for this, but it's all doable, just multiplying things out. You get nice, simple formulas out of it. Well, relatively simple formulas using fairly standard results. And it's little beyond what we do for the finite case, the Dirichlet LDA model or the gamma Poisson model of Canny in 2005. It's a little beyond that. That's an example from my report of all of the non-zero rates, what they look like. Oh, there we go. So that's how far I got in writing this up. As I say, I've got a longer report that does the full detail for those of you who want to see a lot of the derivations and stuff. In that I include, I've tried to include simplified versions of the derivation. So rather than waving my hands and pointing to some complex theorem buried in a book that none of us can read, I've digested the result and given it there in a fairly simple way, because in all of these cases, apart from these model equivalences, all the results are actually pretty simple. As I said at the beginning, it's not really that complex, it's just written up that way. My favourite examples, this was another rant I was going to add. There's a whole series of papers by people. They start off with beta process and gamma process, and they give you 2 pages of process theory. And then they say, oh, well, to implement it, we're going to do a truncated version. And so they throw away all of this. They ignore all of that theory. And then they're back to the good old gamma Poisson in the finite case that people have been doing since the year 2000. And they implement that. So that happens an awful lot in the community. It's very annoying. Whereas all of this theory is pretty doable and not that difficult. Some of them go to the stick-breaking result. And the problem with that is, if you know about variational inference, tends to push probabilities towards the 0.5. It very strongly pushes probabilities towards 0.5. So if I've got a hierarchy, a linear hierarchy of 200 probabilities, and there's variational inference done at every step, my estimates become very bad. And it really doesn't work. So people doing stick-breaking inference with variational methods, I can tell you now it's not going to work well. But there's ways of doing it that aren't that difficult. All right, there we go. That's it. That's my theory. We've finished way early. That's because I missed out my introductory tutorial. So I hope you didn't worry that I didn't talk too much about Dirichlet's or graphical models. There we go. Thanks.
So, yeah, clearly this Bayesian methods and these graphical models is a fascinating and complex research area and full of maths and a whole lot of things which you've really done your best to to make it a bit more accessible to a slightly more general audience who don't live in the depths of hideously complex equations. And you've managed to distill it down to a 2.5 hour tutorial slot magnificently. So thank you very much.